well, as usual, well, once we have a concept like uniform convergence, so we would like to see some tools, some rules, how to decide whether a sequence or series does converge uniformly or not. And of course, that's a subtle question, but there is a very simple test. And this is often called a Weierstrass test. And the Weierstrass test says that we can do something like, if you remember very in the beginning of the semester, we talked about how to decide whether a sequence converges or not. And we had this approach where we compared it with some sequence we knew about. So that was the comparison method, right? And that's very easy, and it works here equally well. Why not? Because how does the comparison method work? So it says that if I know about some sequence, how fast it works, how fast it converges, and if I know that the absolute values of my sequence are smaller than those, then it must converge at least as fast as well, right? And here we can estimate the absolute values of Fn by some reals, and this will be some suitable real constants. Well, the function values could be complex, who cares? And this should work on all this interval. Then of course, if I take either the sequence itself or if I take a partial sum of the functions, then if I compare how they differ, so I see that they will differ as the constant, well, at most as much. So it's Cauchy with such a speed of decline of the differences as with the numbers. And this says that actually it must uniformly converge at the same speed. Right, and that's the Weierstrass test. So if I have this estimate by some reals, then the series of the numbers, so it must be an absolute convergence, right? Because it's just positive reals or non-negative reals. Then the series converges uniformly. And this was the way how we showed the convergence of power series. We compared the individual items with some geometric series, and therefore by the Weierstrass test we now actually have proved that it converges uniformly. We know that derivative of a power series is again a power series if I differentiate term by term, right? And so it fulfills all the conditions from our theorem in the last talk. And therefore we know that every power series is continuous on the interval. We know that the function is Riemann integrable and differentiable, and everything can be done term by term. So we can always we can swap the limit procedures. So this is very, very nice. So let's make one more comment in that direction, and that's coming back to the function which we had earlier in paragraph, and which is a very nice function, right? Because it's e to minus something non-negative. So the bigger the something is, the smaller e to minus the thing is. So at 0 we complete the definition by 0, and it's the function which has got all derivatives 0. All the derivatives of the function at the beginning are simply 0. So the function must be something which goes through 0, attached to 0 as closely as you could imagine at all, and then finally it starts moving up. Right, and if you go with x to infinity, then it will finally come to 1, right? So it will be such a bump, which is done the other way around. So that was what we had sometimes back, and now imagine that we simply throw the expression minus 1 over x squared into the power series for e to x. So this is what we get. It's a function which would look awful, but we can just change it, just writing minus n into m instead of n. So you see it will be something like a power series, except instead of of going from 0 to infinity with the powers, I go from 0 to minus infinity, just the opposite direction. And I get such a power. And this series obviously must converge at all points which are not 0. So in 0 it doesn't, right? In 0 it's going wrong. In 0 it's just a difficult thing, right? But in all other points, if x is non-zero, it will work. So, and this series gives extremely good idea how it behaves near to the exceptional point x equals 0, right? So we can consider this in a more general way, and that's what people call Laurent series. So the Laurent series are simply power series which go to both sides, to plus infinity and to minus infinity. And it's a Laurent series centered at the point x0, and an are the coefficients, complex numbers in general. And this series is called convergent, or we understand it as a convergent thing, if we can split it into two series. One of them will start, say, at 0 or somewhere else and go to minus infinity. The other one will go to plus infinity. And of course, the existence of the limits doesn't depend on where we do the cut. But so let's say we do it at 0, right? And the importance of the Laurent series can be seen if we look at the rational functions, right? So if we have S will be a quotient of two polynomials. In particular, if we take some root of g, so if it will be an s tuple root, so the multiplicity of the root will be s, then if we multiply the original function by x minus x0, that's the root, to the power s, then we sort of smooth out the singularity which is there because of the root, right? So this will be just having a singularity, no well-defined value, and values just jumping to plus or minus infinity, or in the complex setup that will become completely complicated to understand. So we just smooth it out and we get a regular power series around of that point, right? So it's like here. So actually we see that there will be a power series, and if we divide it back by this guy, then we get it this way. So you see that all the rational functions will have nice expressions as Laurent series. And if we consider the two parts separately, which we can, then of course we can employ the rules how to compute the convergence diameter for a power series, right? So we get some radius of convergence for the S plus, which is just this capital R. Reciprocal value will be the limit superior of the nth roots of the absolute values of the coefficients. And the same idea just goes through with the S minus, except here it will just go the other way around because we are with the negative powers, so it will converge for being further than some given small r. So the small r is the limit superior of the same guy going to infinity, right? And this is quite remarkable, isn't it? Because what we get is, for each of the Laurent series, we simply get two circles. So if it was, say, centered at 0, so we get one circle, so that this one will be the capital R, and another one which will be the small one. This will be the small r, but the small r could be also here. So if it was here, so what you get is we simply get the convergence of both sides on this, say, donut shape thing, because we need to have x which is smaller in absolute value than the big R and bigger than the small r, and that's it. But if it's this case, then there will be simply no x where it converges. So the Laurent series could be not having a convergence domain at all, or it could be such a strip. It could also be like it was with the e to minus 1 over x squared, where it was just 0 where it didn't work, and in all the other x's it did work, right? And I'm drawing it in complex plane, but you can think about the real line only, so it will then be the restriction to this line only of what I'm drawing in the picture. Right, so that's the Laurent series. And here is the theorem about the convergence, which I already drew on the picture. And that's it for this bit of my presentation. So it's rather short, but I rather cut it because I will now come to the completely different story which goes on.